start with Viewstamped Replication made famous by Joran. And this might be hard to believe, but this is going to be a cinematic slide deck. So sit tight and enjoy the ride.
Greetings, Laurice.
Hello.
How are you feeling today?
I'm fine. How are you?
Excellent. Great to be on Showtime. Shall we play a game?
Love to. How about Total Order: Rise of the Replicated State Machines?
Wouldn't you prefer a good game of Viewstamped Replication made famous?
What's that?
It's a game where you design a distributed system for optimal high availability and see if someone can hack it.
Okay, tell me how to play. The stream is yours, and your time starts now.
Wait a minute, Laurice. Are you telling me that Showtime now has a time limit?
Yeah, and the timer started already.
Oh, well, meet the client. Clients are friendly, very friendly. They can be wealthy with bags full of financial operations they want to keep safe. But while they're friendly and while they have bags full of financial operations they want to keep safe, they're also pressed for time. And they don't like to be kept waiting. In other words, they're loaded down with all kinds of valuable things they want to store safely, but they have little time. And that's because the other trouble with clients is that clients come and clients go. And if you're not available for them when they need you, then they might not show up again. But wait, whose clients are these? Why, these are the clients of Tiger Bank, a financial institution whose pillars are the foundation of trust, where the grass is always trim and the trees grow tall. You could even say the sun shines at Tiger Bank, and the vaults are never half empty, but always half full. But Tiger Bank, for all its charms, is still a traditional institution, a brick-and-mortar kind of bank, the kind where you sign your checks on paper. And the clients? Well, the clients are starting to think different. The clients want to bank on their phone. They don't like waiting. They want to be on the line, not in the line. And that bag full of paper IOUs is now a phone full of payments too. What did Tiger Bank decide to do? To keep the grass trim, the trees tall, the sun shining, and the vaults half full? Well, they decided to spin up something called a server, to be like the teller at the bank, but instead of serving walk-ins, it's going to be serving requests from clients' phones. Clients are going to dial long distance into the server through their phones. Say howdy and hi, and then put some of their precious IOUs into a little red bag and send it over the wire. A little red bag called a packet. And Tiger Bank have got a special name for this packet. They're going to call it a request. But the amazing thing they dreamed up with this design is that the clients just put these financial operations into a little red bag called a request and send it off like it's FedEx. The impatient clients don't even need to hang around for their requests to get to the server. They just ship it off and say prego and ciao, and everyone is happy. And this is also going to work great because the clients really like Tiger Bank. And because the clients also know that they're coming and going so much that it's very easy for a client to lose a phone like this, or like this, or like this. Whereas Tiger Bank still has these vaults that are half full to store this new server machine safely. And these vaults are obviously completely waterproof, tractor-proof, and pirate-proof. But the best thing of all is that these half-empty vaults, half-full vaults, even have bonus space for the backup machine. So the Tiger technicians, as a bonus, are going to 2x Tiger Bank's durability. The backup machine is going to copy from the primary server machine exactly on the hour, every hour, using something called a Tron job, because everything happens like clockwork at Tiger Bank. And this copying trick to back up the primary server is also going to use some revolutionary consensus technology called the File Transport Protocol, or FTP. In fact, one of the IT staff became so convinced that this would be most efficient after reading a Hacker News comment. That was the top comment, that it's trivial to use FTP to synchronize your backup with your primary machine. So they're going to connect the primary server to the phone line and let clients dial in and shoot off these one-way requests in little red bags called request packets. And then they're going to have two people sitting in the vault so that if the primary machine crashes, they can just unplug the phone line from the primary machine and plug it into the backup machine. Now, this system was all set to launch when a very fastidious employee at the bank called Mr. McKittrick made the right call and stopped the launch. Because he was a very risk-averse employee. After all, Tiger Bank was a happy place, where the grass was trimmed, the trees tall, the sun shining, and the vaults never half empty, but always half full. If there was a word to describe Tiger Bank, then it would be hard to find a better word than staunch. So Mr. McKittrick said, maybe we should test all this new dial-in service stuff with bonus backup and FTP before we launch. And he began to dial the number of an old friend from school called Bishop. Now, Bishop was a cool character. He was called Bishop because he was a chess player and because he had an interesting line of work. Banks would call Bishop up and hire him to think 3 moves ahead, to find ways to break their new dial-in servers, to make sure that no one else can break their new dial-in servers. And Bishop was cool, not only because he thought different or because he looked like he listened to jazz, but because one of his bank jobs had even been made into a movie about running shoes. Of course, it didn't take someone like Bishop long to think through what was wrong with the bank's new dial-in service system. In his report, Bishop wrote, and then underlined in red, that the new system was not highly available and would keep clients waiting while the technicians reacted to a crash of one of the machines by swapping phone lines to the backup. Bishop understood that the primary server might crash at an awkward time, that it might take too long for the two technicians both to agree that it was in fact crashed, and that the technicians might easily forget which was the primary. Which was just another clue that the system was definitely not fault tolerant and could not be trusted, because the clients were sending requests in fire and forget fashion. To illustrate this point, Bishop evoked the image of the cable monster, a disgruntled telecoms engineer in the neighborhood who would at times play tricks on people who were busy dialing into their servers by rerouting or replaying their phone calls. But in the case of Tiger Bank, if the cable monster in the network were to cut the wire after a client sent a financial operation, deleting it from its own phone, but before the server were to receive it, then all the money in the operation would be lost. And just as bad, If the cable monster were to record and replay these calls, then money would be paid many times over. Sadly, the system was also not durable and would not keep the client's operations safe. In his inspection of the vault, Bishop found a rare breed of beetle that would have been very attracted to the aluminum in the batch of identical hard disk drives that the technicians had purchased for a discount from the same vendor. And so it became evident to Bishop that if the beetles did not get to eating the aluminium in both disks, then a manufacturing quality control issue from the vendor eventually would. But if the beetles did get to a financial operation on one machine, then Bishop would have expected that this machine would repair itself using the copy of the financial operation from the other machine, even if both machines were being corrupted in different places. Sadly, however, there was no such provision for any automated recovery from corruption or data loss. And of course, because backups were going to be taken precisely on the hour, there would always be many minutes of financial operations lost in between backups if the primary were to fail permanently. Unfortunately, the system was also not consistent. And even if the primary were to fail temporarily, when it came back up, its data would be inconsistent and irreconcilable with the backup that had been running in the interim. It was also possible that the technicians might forget to swap the FTP job around when they swapped the phone lines. Thinking 3 moves ahead, Bishop could see a time when the 2 technicians might be in the vault, half awake, with the FTP backup mechanism set to back up to the wrong machine. The clock would strike the hour, the FTP job would run and overwrite the server's more up-to-date data with the older, less up-to-date version from the backup, destroying data on the server and causing the primary server to crash as its files were deleted, which would set off an alarm and wake technician number 1, who would ask, "What?" Then swap the phone lines to promote the backup to be the primary and swap the FTP job around before going back to sleep. Before the clock would strike the next hour, the FTP job would run again and replace the data on the primary server with yet more stale data and crash the primary and wake technician number 1 again, who would then wake technician number 2 with his shout of, "Oh no." The launch would not have been a success. This new system was not a marvel. It would still keep clients waiting to store their financial operations before going out of its way to lose them or mess them up. Bishop emphasized again that FTP is not a consensus protocol. And finally, because this misinformation seemed to be at the root of the problem, in his report, Bishop concluded by referring Tygerbank to a brilliant young student who had pioneered the field by writing, "Call Dr. O." Everyone at Tygerbank was so amazed and impressed with Bishop's report that they paid him a $3,000 bounty in addition to his contractual fee, immediately promoted Mr. McKittrick, and then went looking for Dr. O. He was called Dr. O because he would design original algorithms that would make the suboptimal optimal and the impossible possible, so much so that people would sit up and say, "Oh," especially the professors in his field from leading universities such as MIT, Cambridge, New Hampshire, and many others. Because not only was Dr. O's work original or optimal, it was also so clear and elegant, making the formal ideas informal in a way that was readable and ahead of its time. And when Mr. McKittrick and everyone had flown Dr. O over to the Tygerbank office, and when they had all sipped some of their homegrown, homebrew Tiger Tamarillo, and when they had told Dr. O that their clients wanted high availability, fault tolerance, durability, and consistency, this is more or less exactly what he said. Right, everybody. First, we're going to need more bags. To solve the problem of the cable monster that occasionally eats packets when clients dial into the server, we need a little red request packet bag for clients to send financial operations, yes, but then we also need a little orange reply packet bag for the server to reply and tell the client the result of the request. This way, the client doesn't delete the financial operation until it knows it's safely stored on the server. And if the client goes away quickly before it gets the little orange reply packet, then it can just say hello again and resend the request until it gets the reply. When it gets the reply, then it knows it is safe to delete the financial operation because it's stored on the server in the vaults. And we'll include a little number in each client request packet so that the server can ignore duplicate requests. Speaking of the server, we need to rethink the way we think about what's inside the server. The trouble is, up until now, Tigerbank, you've been using the plural servers, a primary and a backup, i.e., multiple personalities, instead of the singular server, i.e., a single personality, and this is leading you into trouble. What we need to do is take the concept of a server and keep it singular. We only want Tigerbank to ever have one server, so clients only ever see one server. I know what you're thinking, only have one server? But let's take a look at what's inside this new breed of server. We've taken all the expensive big iron and turned it into 3 smaller machines that all work together to appear as a single logical server. We've gone from multiple physical servers to one logical server so that we can have one consistent set of data and be a single system of record. But that's also going to be much more fault tolerant and durable, as we shall now see. To solve the durability problem, let's pretend that the phone line is just always connected to the first replica, replica 0. Then, when the client sends a little red packet to the server, this will arrive through the phone line that's connected to replica 0, which is the primary machine, because that's the machine that's answering the phone line. Now we're going to do a cool magic trick. So when replica 0 receives the little red request packet from a client, before the primary ever sends the reply back to the client, we're first going to have the primary put the little red packet inside another bag, a little blue packet called a prepare packet, and then send it to the backup machines. First, to the next replica after it, which is replica 1. And then in parallel to sending the little blue prepare packet to replica 1, it also sends the same prepare packet to itself, so we can always just reuse the same code path for handling these prepare packets when we receive them. Then as soon as replica 1 receives the packet from replica 0, which because they're in the same vault, it's a split millisecond later, replica 1 in turn forwards the prepare packet onto replica 2, completing the replication circle. While this is happening, replica 0 has finished storing the packet and sends an OK packet back to itself. Again, just so we can always have a single code path to handle the OK packets we receive. Then replica 2 also sends the OK packet to replica 0. And now replica 0 can reply back to the client, knowing that the client's request is safely stored on 2 replicas, so that even if a whole replica machine is dropped in water or destroyed by a tractor or stolen by a pirate, the client's request will not be lost, but will be durable. Notice also how small these little OK packets are. They're so small, they're very lightweight. And also see how, while we pass the prepare packet, each replica also sends the OK packet directly back to replica 0. But why do we want to reply before replica 0 receives the OK packet back from replica 1? Let's take a look at how we count these OK packets with something called a quorum counter. When the client's request arrives, we start to replicate it to ourselves, and then to replica 1, and then replica 2. So we haven't received any OK packets yet. While this is the case, we might decide to resend the prepare packet, and perhaps we might leapfrog replica 1, just in case it's crashed and can't forward for us. But then at some point, we receive both OK packets. And then we can see that, okay, replica 1 is either slow, maybe because the hardware is slowly failing, something called gray failure, or might be temporarily slow, maybe the solid-state drive is doing a garbage collection. Or it might even be that replica 1 has just crashed. So it makes sense that we reply after 2 OK packets, because this way we can make TigerBank super fast without slowing down for the slowest replica. But why do we do this past the prepare packet game? Why don't we just have the primary machine itself send the little blue prepare packet to all the other replicas, like so? Because, as Dr. O told TigerBank, it's not optimal. And here's why it's not optimal. Imagine that replica 0 can receive 100 packets per second and send 100 packets per second. If replica 0 now has to forward a little blue prepare packet to the other replicas, and if the server contains something like 5 replicas in total, then this means that replica 0 has to forward the big prepare packet 4 times, which divides the number of packets that replica 0 can send from 100 packets per second by 4 and becomes a bottleneck. And this is also not optimal and even makes the logical server unstable, because this also places more load on replica 0 compared to the other replicas. Let's count how the messages are sent. All the replicas receive 1 big prepare packet, but then replica 0 is the only replica that sends 4 big prepare packets. The little blue OK packets are so small that they don't make much difference. So we can see that the load on replica 0 is really driven by the big prepare packets it has to forward to all the replicas. And this load is unevenly distributed. And that's not optimal. Let's see now how our pass the prepare packet game does if we count our messages. Again, all the replicas have to receive the big prepare packet, so that's 1 for each of them. But then the magic happens, and each of them play their fair share of sending the big prepare packets to other replicas. And we can already see this is optimal, because the load is now evenly distributed, no matter whether a machine is a primary or a backup. And so, said Dr. O to everyone at TigerBank, this is how we solve durability optimally. But what about order? Clearly, the client's financial operations might depend on other financial operations, and we don't want to allow overspending. Here's what we need to do to make sure that all the replicas get the financial operations in the right order. First, we must understand that clients might say hello at the same time. Here's client A with request 1, client B with request 42, client C with request 100, and each of these are the number of requests per client. So this is client C's 100th request. They are a centenarian. And then client A's request number 1 gets replayed by the cable monster. The problem we want to solve is how to get these requests into the log in exactly the same order on every replica, so that we're putting these little blue prepare packets into the log like this, and like this. That almost looks like my uncle's old recipe, curry in a hurry. Back to order. Because we have replica 0 as the primary for now, this is pretty easy. We just have replica 0 keep a number in memory called the prepare operation number, or op number for short. Then as each client request arrives, we assign it a number. Let's say that replica 0 has already processed 699 ops. So our op number is at 699. Then C arrives first, so we append op number 700 for client C to the end of the log. Then A arrives, so we append A's op to the log as op 701. Then B arrives, so we append B's op as op 702. And then A's first request arrives again, but we just ignore it because we can see that A's first request is already in the log. Now I know what you're thinking, predicts the prescient Dr. O. How do we go from this log to executing these financial operations and acting on the client's financial instructions? Simple, we use a functionator. Yes, a functionator. A functionator is nothing more scary than a simple function that will take all your account balances and the current financial operation you want to execute and then return the result, which the server can then send back to the client in the reply. And really, the beauty of the functionator is that it is what it is, a simple bring your own function that you could change to any function you like. And so we return again to our question. Now that we have a beautifully pure functionator, which is simply a function, how do we go from the log to executing operations through our function? Simple. We have the replica track another number called the commit number. Then if our commit number is 699 and we see that we have replicated op 700 to enough machines, we simply run op 700 through our functionator and bump our commit number from 699 to 700, and so on, and so on. And there you go, said Dr. O. Fault tolerance, durability, order, even a functionator. But how do we swap the phone lines and the primary replica automatically? Well, Dr. O said that there were at least 2 ways to swap the phone lines, depending on a number of factors. And so Dr. O introduced them to somebody just as special, who was the professor, who taught Dr. O how to think about all these things and how to optimize and make trade-offs. Now the professor was elegant in every way, and in fact so elegant, and had contributed so many elegant ideas to the field, that a Turing Award had been given to the professor to say, thank you for the amazing things that taught people how to think and see the world of computers in new ways and speak new languages to computers, languages even written by the professor, and all so that people could learn to express new ideas that the professor had also discovered. In fact, the professor created programming languages that were so incredible that her programming languages, just like Bishop, would go on to become movie stars in their own right, where, just like her Viewstamped replication, they would strive to create the perfect order and become famous for saying things like, "Greetings, programs." But despite all the fame, they never forgot about the professor and always took the effort from time to time to send a short pager back from the grid just to say, "Thank you, Professor." Now, in addition to Dr. O, the professor had also served as Jedi Master to a young Skywalker called the DJ. He was called the DJ because he was a disc jockey who would play at all the weddings for distributed systems gurus getting married, where he would play 70s, 80s, even 90s distro music, which was the kind of music he loved to play. He was also called the DJ because his name was James and because he was a doctor who could create the most awesome remixes of any kind of distributed protocol. And he could create these remixes not only because of the professor's help, but also because he was a wizard with a special magic pocket. Now, to decide how to swap primaries automatically, to decide which replica should answer the phone line, the professor and the DJ had in fact remixed one of Dr. O's protocols. And this remix was so amazing, it was basically VR, that is, virtual reality. Not only because it gave each replica a way to see how the primary replica, who the primary replica should be, as Dr. O's protocol had also done, but because it was so magical, you could even predict who the next replica should be. And all by adding something as simple as an in-memory number called the view number. The way the magic worked was that if a replica's view number was 0, and then if you took the mod of the view number 0 by the number of replicas, then you could immediately see that the primary would be replica 0. And if that was replica 0's view number, then replica 0 would answer the phone, otherwise it would just let it ring. You can see now that all of a sudden we can have 3 phone lines coming into the logical server. Clients can call any phone number they like, and then each replica can just decide whether to answer their phone depending on their view number, who they see as the primary. So if the view number is 1, then replica 1 would see itself as the primary and answer the phone line. And if the view number was 2, then replica 2 would answer the phone. To add to the magic, this would also have the effect of freezing to ice any previous views. So as soon as a replica learned of a newer view number, it would stop answering the phone for that view, and the old view would gradually freeze over. Then as the view number went higher and higher, it would just rotate the primary across the replicas and back to replica 0, who would then answer the phone again. The two technicians were so excited by this virtual reality, they wanted to know more. And this is, more or less, exactly what the DJ said. We always start with replica 0 as the primary, because we always start with a view number set to 0. If the other replicas stop hearing from the primary, they stop getting prepare packets from the primary, then eventually they decide to bump their view number. If replica 1 notices first and goes, then it bumps its view number from 0 to 1, and it also freezes its view number so that it doesn't answer the phone just yet, until it knows that enough of the other replicas also know what the new view number should be. Then it tells the others to start the view change and bump their view numbers to 1, and when replica 2 gets the start view change packet from replica 1, it bumps its view number to 2 and also freezes and sends the start view change packet to all the other replicas. Now replica 2 can already see that it has bumped its view number to 1, and it also knows that replica 1 has done the same, because, as you will remember, it received the start view change packet from replica 1. So it knows that two replicas have sent start view change packets. And then replica 1 receives the start view change packet from replica 2, so it also knows that two replicas have bumped and frozen their view numbers and set them to 1. So now they do something special. Replica 2 sends its latest op to replica 1 in a single packet, and this op includes the cryptographic checksum of the previous op, and so on, like a daisy chain or a hash chain. It only needs to send the latest op, which is op 800 for replica 2, so it sends it in a single packet to replica 1, like this. And then replica 1 can see that it only has ops up to 502, whereas replica 2 has op 800, so it sets its latest op to op 800, and then it asks replica 2 for the other ops to catch up. And then when replica 1 is all good to go, it unfreezes its new view number, and then it tells the other replicas to unfreeze their new view for view 1 and start the view, and it does this by sending a start view packet. And if this whole repair process takes too long, if replica 1 is more than a few milliseconds behind or a few hundred, then the other replicas will just do the same view change and bump their views and so on, and we'll get to the replica that's got the latest log. So this repair really doesn't delay the view change at all. And this start view packet, which the other replicas receive, then contains just the latest op 800, again in a single packet. And this is enough with the daisy chaining for the other replicas to catch up and then unfreeze their views. Having completed the view change, and all of this automatically within a few split seconds, replica 1 begins to answer the phone as the new primary. And so with the normal protocol and with the view change protocol in hand, the technicians quickly got the new system going, and McKittrick brought Bishop back again, and Bishop helped to bring these protocols to production with some simple designs like the packet bus, which was really just a way to keep all the packets and phone lines neat and tidy and provide a simple way to send packets from a client or replica to another replica just by knowing the number of the replica, or to send a packet from a replica to a client just by knowing the unique 128-bit ID of the client, without any IPv4 phone lines getting tangled throughout the protocol code. And also enabling multipath routing, where the client can send a message to one primary, then a view change happens, and then the client gets the reply straight back from the new primary. How cool is that? Much better than RPC. But what the technicians really liked was the design they came up with for the replica. The replica was just the code that would be run on each replica machine to execute what had now become known as the Viewstamped Replication, or VSR protocol. The cool thing with the replica was that it only had two public methods: a way to tick the replica, just like you would tick the second hand of a clock, so you could tick the replica as fast or as slow as you liked, and a way to pass a packet to the replica. With a simple design, the replica was now like an automaton that you could play, rewind, or fast forward exactly the same way every time. These designs for the packet bus and replica, in turn, allowed for the creation of the Whopper, which simply stands for Viewstamped Operation Replicator. The Whopper was a whopper of a deterministic state-checking simulator that the two technicians could run beyond the clock to speed up time and simulate all kinds of ways that clients might greet the server or that beetles might eat the aluminum material inside the hard disks. So that even if these beetles evolved into little techno beetles called tiger beetles, the Whopper would be able to check that everything worked, and most important of all, that everybody was happy. And so it happened that Tiger Bank remained an institution whose pillars were the foundation of trust, with the grass trim, the trees tall, the sun shining, and the vaults never half empty, but always half full, with the exception that now the phone lines were humming, the clients were calling in transactions like crazy, and the two technicians, well, they thought this was all kind of magical. Grazie, Loris.
Wow, Joran. You really gave an amazing talk. Thank you very much. I'm sure people have enjoyed it a lot. Also, I'm reading the comments. People are enjoying the references a lot. That was an amazing talk. So let's see if people have questions. Let's not spend too much time in the Q&A because we have a lot of things to do. But if anybody has any question, you have very quickly a few seconds to type them up, and I'll reroute them to Joran. In the meantime, let's see, what question could I ask you? Do you are meetings at when you're like developing Tiger Beetle, are meetings like this? Like usually people prepare slides, boring slides. At best, they have transitions like full animations. Like, do you do this stuff also at work every day?
You mean Tiger Bank, Loris?
Yeah, Tiger Bank.
Yeah, no, absolutely. We do these meetings just like this. And in fact, this is what we'll be using for our next meeting as we all discuss Dr. O's principles and the DJ's ideas and the professor's ideas. But no, this is a one-off. we don't do it like this. I would love to. It was so much fun just drawing these sketches. I'm a terrible drawer with pen and paper, but I used the iPad for the first time, and I felt like Picasso. So hopefully we'll use these in future meetings.
The visual style was very good. I enjoyed it a lot, so I think people have enjoyed it too. So it seems that people are pretty satisfied with the explanation. You were very thorough. You went from the basics. Yeah, banks sending. Can you imagine banks sending financial transaction information via FTP? That would be crazy. Like, imagine if the world was really like that.
I think today they don't use FTP anymore. It's just SFTP, so it's the secure version. You know?
Yeah.
But I've seen quite a few of them still do that the way they send their data.
Yeah. Oh man.